Hello everyone, and thank you for joining me. So my name is Gökhan Öner, and I am a senior solution architect in Hazelcast. So I'm going to be presenting you our stream and batch processing engine, Hazelcast Jet, and also we're going to be going through a little bit of a stream processing history, and I'll be sharing you some demos. And also we're going to be talking about the DAG API, which is the foundation of our stream processing engine, and we're going to be also showcasing how the DAG API can help you or help the distributed processing systems to scale up and scale out the jobs. So, first of all, why stream processing, or why should be bothering the stream processing in the first place? The thing is that maybe in the days, like there's just online systems, you have a request that you need to reply, and there's a response for that. So there may be no time limitations, or it is okay to reply in a couple of seconds, and there's no, the volumes are generally low, and the latency could be high. So there's no, the real-time processing or whatsoever, because this is a request response system. But then, when the data volume is getting high, so we started to process the data in batches. But the thing is, with the batch processing, we have data coming in and data is going out, and the data in big volumes. But again, the latency is huge because you're storing the data in some time, and then later in the day, maybe in a couple of days or in a couple of hours, you're coming and processing that data for your purposes. And when you need to process the data for another purposes, then you need to go through all the data again. So this means the latency. But with the stream processing, you have the ability to process the same data while the data is coming without storing the data, or maybe storing the data but don't look into the whole data as a batch, but as a flowing data, and process it with the low latency. So this is why we need the stream processing, because we have a data somewhere or multiple sources data coming, and we need to process this data fast enough so that we can have some meaningful assumptions through that data. Maybe this will trigger our next business processes or next business decision, which needs to happen in a couple of seconds or maybe less than a second. As we said, you can use it in the real-time analytics, fraud detection, pattern matching, pattern detection. If you have an ETL that you're using for batching, but you need it to real-time ETL, then you need a stream processing engine. Also, if you have a continuous data, let's say if you have 1 gigabyte per second data, which means it's like 86 terabyte data per day, which means that you either need to store all this data and calculate a daily result from that, or you need to process this 1 gigabyte data in each second, which is, I believe, simpler. So when we are talking about the stream processing engine, we as users have some expectations, or at least we should have some expectations. What are those? First, we believe that it needs to offer us a high-level APIs. For example, mapping the data, because you have a data, but you need to convert this data maybe to something else based on some decision. You need to be able to filter the data or group the data, or maybe run some simple or complex aggregations on top of the data, or join the multiple streams of data together, right? It needs to be able to offer your connectors to some stream and batch sources like Kafka or HDFS. Also, it needs to give you an API so that you can implement your data pipeline as a job and submit it to the system, so you can store your pipeline later and maybe change it for changing your algorithms or your aggregation function, and maybe resubmit it based on your business requirements. It should execute this pipeline in parallel in a distributed environment, which means that if you need more resources, because maybe you see that, okay, I'm processing this data, okay, but I need faster results, then you can go and add some new nodes to your processing cluster and needs to scale out for you without doing anything. It needs to be fault tolerant, meaning that if any point in time, if you like lost connection to your data source or the sink that you are writing the result, or something happens in between, like a network, due to the network and any other problems, that it needs to be fault tolerant and it needs to go through back in time, maybe automatically, and restart the job from the latest save point that it's being created for you. And also it needs to give you some monitoring API or some monitoring solutions, so then you can go and search for your jobs and what is the results of them. So just let's go through the evolutionary steps quickly. So how this stream processing idea evolved in time. So I decided, we generally divide it to the three generations. The first one is actually the good old Hadoop, so MapReduce. So it's actually come from the Google's white paper and then the MapReduce paper, and the Apache Hadoop then founded in 2006. The thing with the MapReduce, as you know, that you are storing huge data somewhere, and then you are running a simple mapping and reducing task on top of this data. But this is, as I said, this is just the first generation, and it is limited for what you can do with the data. If you need to change your reducing function or the mapping function, then you need to go through all the data again and again. So then in the second generation, we have the Spark. The Spark is actually started in the Berkeley as a lab project. So here is the design is that make this MapReduce to make it like wider audiences can use it, just not just with the mapping and reducing, but also putting some functions like grouping by or like unions and joins. So it is again batch processing here, but it is not just mapping the data or running a simple aggregation. That it gives you the possibility of grouping your data or maybe joining different batch or sources of data together. And then again, Spark evolved and became Spark streaming, because now we are talking about, again, this is not still second generation, because it is not an actual stream processing. What it is, it was actually the stream as a sequences of micro batches. So it is being done with this immutable data sets and what they say that these streams. So it just you can process the data in small time frames, like maybe 1 second, and then all these processing results represent a kind of a stream of data, and then you can process these results. But after that, Spark also moved to data frame and tungsten, and then it will also, and now we can also tell that it's also a third generation streaming engine, which is continuous streams. So all of them, actually, they are DAG based, directed acyclic graph. It is actually, it's a real streaming. It's not micro batching. It's not like collecting the data for a small amount of time, like a second or a millisecond, and then processing it all. It's actually capturing a streaming data on the fly. They also support batching, but batching is actually a streaming with bounds. So these systems are designed as a first-class stream processing engines with batching capability. In the previously, as we see in the second generation ones, they are actually processed, designed to process batching data, but reducing the time for the batching, so you can actually act like a stream-like solution. So this is the difference. So it also came again with the academic papers, and also, as you see, there are lots of framework currently uses this DAG-based APIs. Apache Storm is one of them, Twitter, Heron, Filling, Kafka Streams, Hazelcast Jet, which we'll be talking today as well. So lots of the mainstream solutions currently is considered as this third generation DAG-based streaming API. So, any questions so far? No. So what is Hazelcast Jet then? The Hazelcast Jet is an in-memory distributing computation engine built on top of Hazelcast in-memory data grid. And it's using, as I said, the directed acyclic graph to model your data flow. So if you don't know, I don't know if anyone heard Hazelcast before? IMDG? Okay. So if you know Hazelcast is an in-memory data grid, like a distributed cache, just a simple example, how can you use Hazelcast to access the data and etc. And all these different features like, distributed implementations of maps and queues and some other stuff, atomic, long references and etc. It's just a single embedded jar. And what Jet does is, along with all this feature, what Jet does is Jet uses the IMDG as a core, meaning that for the clustering purposes, for data storage as in memory, it is using the underlying IMDG features. But on top of that, it created a distributed data processing engine so that it can process the data in memory and it can store the data result or partial result or the snapshots in memory through Hazelcast IMDG in the background. It both supports unbounded and bounded data processing. It's a relatively new project compared to the other ones because it started in 2015 and the first public release was in February 2017. And since then we are releasing quarterly. Again, it's a single embedded, single embeddable jar file with no external dependencies. Of course, when you are decided to use accessing systems like Kafka and etc., then you need to have the dependencies of those systems, but the engine itself doesn't have any dependency to any other third party. And it's JDK8 based. So in this case, when we say the distributed in-memory kind of stream processing engine, we are actually saying that the performance, we are talking about the processing engine, the performance of the engine is actually scaled. So when you need more performance, you can add more nodes, and it will just scale for you. You don't need to worry about scale itself. It is the job of the Jet. It is elastic because it can also do the same thing while you're running the operation. So starting from the next version, you will have to pause the job and restart it after you add a new node. But with the next version, it will be available this month, so you don't need to worry about that anymore. So you just add new node to your clusters. All running jobs, when they see a new node is joining, they will be sending to the small tasklets to this new joining node so that you can scale out easily. Data is stored in a partitioned and in a replicated manner, which means that even though you lost a node, a processing node, you're actually not losing a data, even though it's a partial data. Why? Because this data is already stored in another node as a backup while the processing is ongoing. So what happens? This other node promotes this result as a primary data, and the computation continue from the latest successful snapshot. Of course, we have different levels like exactly one processing, at least one processing, or just the best attempt processing. But depends on what you need. You can just set these levels and make sure that you don't lose any data in case you lose a node or another failure. And as I said, no single point of failure. So this is Hazelcast IMDG. It is the core for all the foundations, so it can use we can use all the features that Hazelcast IMDG has. And the Jet is on top of that using the DAG API. It can connect to any streaming sources. The current implementations, I guess, like the Kafka streams or database events via stream CDC or any sockets, just raw sockets, or as a batch the database or HDFS or any other Hazelcast IMDG store. For example, you can use the IMDG map as a source, both as a batch source or as a streaming source. So you can actually, while someone is updating your map, you can have a job that is automatically take that updated value and do a streaming job based on that value. And also, other than that, you can, inside the jet, you can do all sorts of aggregations or operations that you want to do with the data itself, which we're going to be seeing in a couple of demos. And the output could be any of those systems or whatever you are imagining. We have some built-in sources and sinks, but also we have sink builders and source builders for you to define how to read the data from a certain data source, which could be a batch or a stream, or write it. So sink builder are much more easier to develop, because when you are writing the data to somewhere, you don't need to worry about the concurrency, and if you are reading the data from a single node or multiple nodes. But while you are reading the data from a data source like Kafka or, for example, database, so you need to also think about if this is going to be running on a single node, or it's going to be running on just a single instance or multiple instances, and etc. So as we said, it goes beyond IMDG. Like, we already have lots of features. As I said, at least one and exactly once processing, what it does, it just creates snapshots while processing the data, and these snapshots are also stored in memory. So in case you lose the data, or in case any kind of a failure, when the systems get back online, we go to the latest successful snapshot and continue from there. So we are making sure that you don't lose any data. But of course, it assumes that your source who is sending the data is also smart enough, like Kafka, for example, can tell us where we stopped lost, and we can continue from that point. And as I said, it's elastically scales. And also, we have a Lambda support. So while you are coding your pipeline, you can use Java 8 Lambdas easily, or what we call it distributed Lambdas, which is technically the same thing. So if anyone has questions, I can answer. Yeah.
The question about snapshots, are you storing them in the persistent storage or in memory?
So the question is, where are we storing the snapshots, right? So currently, we are storing them in memory, but Hazelcast in memory maps have the ability to define them as a map store, which could be a data store, or which could be a, let's say, in an enterprise version of Hazelcast, we have a feature called hot restart. So you can technically store your map on a disk file to fast access. So it could be the option also. Yeah.
Is it based using kind of like a batch write or something, which IMDG already provides, or is it like in this solution in Jet, or is that something which is a little bit faster?
So writing to
IMDG.
So the question is are you using any batch writes to IMDG to fast access? So it actually depends on your job definition. So if you want to write the data as in batches, so you can create a configuration, or you can create a job for that. But if you want to read, or if you want to write all the data while the data is coming without waiting to see the updates, you can also do that. It depends on how your job is configured and how they're updating the IMDG. It's totally up to you. So let's see this Twitter cryptocurrency sentiment analysis demo. Let me see if I can show this for you, or let me go, if I can go to the presentation mode. So let me first show you this one. So what are we doing here is that this Twitter cryptocurrency thing. So we have a, this one is actually one of the demos that we have in our open source repo. So what we are doing here is that we are reading from the Twitter stream via Twitter API, and then we are looking for some popular coins, and then we are using a natural language processing library, which is Stanford NLP machine learning library. And with that library, we are actually trying to get some sentiment score based on what people tweeted. So the job itself, or the DAG visualization of the job itself, is as follows. So we have a Twitter data source. We are reading from there and adding a timestamp. Then we are converting, because the Twitter gives in the stream there are many tweets. So we are flat mapping it. It's just converting as a stream of tweets. And then we are just doing calculating a score based on, actually we are running an operation. In this case, it's just a score calculation, which is done by this NLP library. And then we are grouping by the coin name. And then we have 3 different stages. So this is a single job, but inside the single job, we have different forks. So this one is just calculate the 5-minute average with the event count. This one does the same thing for the last 30 seconds, and this one is for the last minute. So you will have 3 different results and written to IMDG. And the result of this, or the output of this job, will be something like this. So we will be seeing something similar. So let's go and check the source code and then run it and see the result. So is it the Twitter one? Let me see. So this is the other one that I will be showing you. I think this is the Twitter one. Yes, this is. I think we can see it, right? Perfect. So,
close the left.
Sorry?
The left file.
Okay, cool. Let me see if I can do that. Perfect. So, what do we have? We are building a pipeline. We don't need anything for that. And then we are starting a single node Jet instance, just like this. So this is our processing instance. And we are giving that pipeline as a job and then waiting for the result. This technically join means that wait for the result, but since this is a streaming job, it just wait there indefinitely until you stop the application. So what is our pipeline is actually, so this is the source code of the DAG job that we see just a second ago. So here we have some properties for loading the data from a Twitter source. So we have a Twitter stream source which read the data from Twitter, which we can look. Then what we are doing the same thing that has been written there. We are adding a timestamp. We are doing a simple flat mapping operation, which is just converting this multiple tweets to single tweets, just basically split them. And then we are doing, okay, this is our the sentiment analyzer, which using the NLP framework to analyze the sentiment. And how it is analyzed, okay, it's using this calculate sentiment method. And then we are grouping by entry key, because here is the key is the coin name. Then I have a streaming job here. Then I have an aggregate operation. In this case, I have 2 aggregate operations combined together. One is average operation based on the value of the sentiment score, and the other one is just counting how many tweets there. And using this aggregate operation, I am creating different windows here, which is sliding windows, as we see. One is 30-second window slided by 10 seconds. So I will have a result for the last 30 seconds. But for the next 30 seconds, I'm not going to be jumping to the other 30 seconds, but sliding my window for 10 seconds. So this will be the 30 to 10 seconds, 60 to 10 seconds, and 300 to 10 seconds, like 30 seconds, 1 minute, and 5 minutes. And what I do, as you see, I am giving the same source or same operation here, using different windows, using a same or different aggregate operation, and draining to different sources, and then after then returning the pipeline. So even though there is a multiple operations, it is just one single job. doing all this operation. So you don't need to create different jobs for that. This is just a one job, but different forks inside the jobs. So let's run it and see how that works. So when we run it, I think I cannot increase the font of this, but let's see if I can. Yeah, it seems that I can. Okay, so when you start the job, we print a DAG version of the job. So this is the job pipeline that we say is a pipeline API that we say, and this is the DAG virtualization or DAG version of the job. And we see that our 30 seconds, last minute, and last 5 minutes data is just populating. So it will be printing out for each 10 seconds, 15 seconds, and this is a real-time data. So I'm just connected to the Twitter using my API keys and getting the data from Twitter as we are talking. So I don't need any special infrastructure to run this, just running on my laptop. So I can create multiple nodes of Hazelcast Jet on the same laptop or on some multiple nodes. So here I'm just using kind of an embedded mode, which means that I am submitting the job right inside the cluster. But you can also do the same using a Hazelcast Jet client. So you can have the processing cluster somewhere deployed, and you can have a client application which is connected to the cluster, which is the same, using the same API, and submit the job to the cluster. So as we can see, these numbers are just the what this NLP library scored. That this is actually showing the sentiment or how people feel, and it seems that I did this demo like a couple of times, and I never see, or I just see positive results maybe once or twice. It means that people are actually not happy about how the Bitcoin or how the cryptocurrencies are doing in general, it seems. So any questions on this one? No? Perfect. Let me stop this one, and then let's see. Here, perfect. So let's go to the slideshow. So let's go to where we stop. Okay, so we talk about DAG based processing, but actually what is DAG based processing? So it's actually used to model how we're going to be doing the computations. Okay, so these are called as vertexes. They represent a step in the computation. So it's actually a generalization. You can think of a generalization of a map reducer. Instead of saying, okay, this is a mapping step and this is a reducing step, you're saying that, okay, these are the steps that I want to go through, but I don't know what's going to happen inside this step, but you as the user will tell me what I'm going to be doing inside. But this model will allow me as the system to model your job as to model your job so I can scale it and run it on a distributed fashion using as much as resources as I can. And this also supports both batch and stream processing. And other than Hazelcast Jet, as I said, lots of different frameworks are also using it. So let's go through a simple example and how can a simple job or a task, in this case a batch task, can be converted to a DAG API, and we see what is going on in behind the scene. So imagine that we are living in a single-threaded world and we are trying to do a word count example. So this is what we do. Like we have a long string somewhere. We are just splitting it with the white spaces. I have a map for the counts for each word, and I just split it and just compute or increase the count. So this is what I do. So how am I going to convert this to run on a distributed environment? So if we represent the same job as a DAG job, or with the DAG API, this is what it is. So I have a source. Source gives me a text. So that I have a vertex do the tokenization. After this vertex, I have the word, and then I have this aggregate job, which actually holds the previous state of the aggregation result, and then convert this to word to count pair, and then I sync it to a hash map in this case, or a result set, whatever. But as I said, since this is a single threaded, each vertexes needs to run one after another, right? They can't run in parallel in this case. But what can I do to make it run in parallel, let's say? Well, I can put some queues in between here, and let's say that, hey, okay, I have multiple threads that I can use, both of them, or many of, Then what I can do, I can have one of the threads do the tokenization constantly, and the other thread do the aggregation constantly, and I can put some concurrent queues in between, and each vertex, what it does, this one just split the text and put the word to another queue, and this will listen to that queue and do this aggregate operation and increase the word count. Then I can just convert it to a parallelized version. But again, it is just, I'm using just 2 threads. What if I have more CPU powers, more cores? What can I do? Okay, well, I can be smart enough to not to give the whole word to a tokenizer, but instead I can read the source line by line and give each line to different tokenizers so that they can run in parallel, right? But the thing is that the result needs to go to the same aggregator. Why? Because I need to have to combine the same results for the same word. So maybe the word Paul is in this line and also in this line. So I need to make sure that my aggregator has all the data set, all the results from the previous aggregations, so I can combine on top of it. But what if I need to parallelize this one as well? What do I need to do? Well, then what I can do, I can use a partitioning algorithm or a way of partitioning data based on my word. And I can say, hey, okay, I know that I need to hold the whole data, whole aggregation result, but let's say I'm smart enough and saying that, hi, if it's a word Paul, then I can just run a simple algorithm, find the partition, find the hash key, and say, okay, based on this one, if the result of this hashing is 1, then I can send it to this one. If it's 2, then I can send it to other one. Then I make sure that the same words are sent to same aggregator. And then later on, here, I can combine this result set while writing to my sink there. So this is further parallelization by partitioning the data here and the processing. But the thing that we need to ensure is that same words needs to go to the same aggregator all the time. Okay, so this is just a single node or a single JVM. What if I need to run this through multiple nodes? What do I need to do? Well, then I need to have a distributed partitioning schema, first of all. And also, I have an additional combination step here. Why? Because of this. So I had all this in my previous slide for a single node. But then when there's 2 nodes, I need a way to combine the results in each node. So what can I do? Okay, I can do the same thing. I can read the data. In this case, if it's a file, it is not, it's not easy to read a file from different sources, but assume that you have multiple files that you need to read. Then in this case, I can make sure that, okay, this node reads the files starting with A, let's say, and this will be reading the files starting with B or some other logic. And I'm making sure that each of these are, accessing to a different source. And then I can do the same here, accumulation. But here, in the adding another combine step, I can make sure that each words, or each, in this case, partition words, go to a single combine step. If there's a Paul here and Paul here, they all go here in this case, because this knows this, in this case, this cluster knows which combine step holds the initial results for the Paul, and it needs to send the data there. So this is how the DAG API, behind the scene, split your data or split your processing job to these units, so that it can benefit from the all resources, all CPU resources in the machine. But of course, this is done by the way that you are defining your job. In the previous example, for example, when we do a group by based on a key, we are technically saying that, hey, okay, I'm grouping the key, so be smart enough to combine the results of the different keys on the different accumulators, so that use as much power as you need it there, because it's already there. So don't use just a single core or a single thread or a single node to combine all the results. Use all of them and create as many resources as you need it. So how is the performance? So this is a performance benchmark done while the Jet was in 0.4. I think it was a couple of months ago, like maybe 6 months, 7 months. So it's a combination between Jet, Spark 2.1, and Flink. So for the time being, just don't see this one, the yellow one. So what we are seeing is the word count benchmark is actually what I described here. So it is being done for different subset of data. For example, this one, the first one is 64 gigabytes data, which contains 1 million distinct keys. And we have another one like 640 gigabytes of data, again 1 million distinct keys, and all these different use cases. And here is this axis shows the processing megabytes per second, so which means that the higher is better. And as you see, the Hazelcast Jet is mostly 2 or 3 times faster than even Spark or Flink. So all specs of the test, the environment that's been running in the Hazelcast Jet web page, and it's open source, so you can just access that and see what is the machines that is being used, which features that has been available during the benchmark. So again, what about the latency? So this is another benchmark, because when we say latency, the latency in the batch job it doesn't make too much sense, but in a streaming job, it does. So it is a streaming job. It's a streaming trade monitor. It's actually a background task continues to write data to Kafka, and there's this job, just read the data from Kafka with a sliding window and just count how much data that it read in that period. And this axis shows the latency. What is the latency there? So as you see, the Jet again has the lowest latency. The interesting part is that when you push more data to Jet, the latency gets lower. Of course, until certain extent, because of some mechanisms that we are using in the behind that I'm going to be showing you in a couple of minutes. But just returning here, so these all cases, other than this green one, this shows that if we read the data from a Hadoop system or a file system or whatever, what if your data is already in memory? In this case, for example, if you store the data, let's say each line, in memory, in a Hazelcast IMAP, so this is the throughput that you're going to be getting at. So if you already have the data in memory for some other use cases, then you can benefit from the Jet further, because it knows the IMDG. It's built on top of it, so it can access the data faster than anything else. Any questions? Yep.
So the throughput slide.
Yep.
When you're comparing Spark, typically the argument for Spark being slower than in memory systems is that you have to move the data. But presumably here you're reading from Hadoop. It's the same. You have the same overhead of that movement.
This latency one or the throughput? Okay, yeah, it is the same. So we are not storing anything in memory. Only thing here in memory test, this is why I told you to don't see this one in the first place. So all tests use the same data set from the same source, Hadoop, and then just runs it. So it's technically the same thing, same job running on different systems. So I'm gonna be going through fast because I have another demo that I'm going to show you, and it seems that I have less than 10 minutes, I suppose. Okay, Good. So as I said, so we have actually, let me go through that and show you. So we have two APIs. One is the high-level API that we just see, which is the pipeline API. So this is the same job that does the word count. This is the API that we look through this Twitter example also. This is our high-level API, which is very similar to Java Util Stream API. And this is the low-level API, which is the DAG API. It's more verbose, but it has more capabilities, at least for now. So, but everything that is being written in the pipeline API is actually converted to this DAG API in the background. So, and this is why we see a DAG output of the job itself. So it's been converted to DAG and it's just been printed there. So you can see which steps is being processed there. So it's distributed to the whole cluster. Each node actually have the whole graph of that, but it doesn't mean that they will be running each of the vertexes there. They know what to run, but it is up to them or the resources there, which parts of the data or which parts of the processing task that they will be running. So the processors we have that, let me show through here. So let's assume that you have a producer vertex and a consumer vertex. These are this could be one of them could be just the splitter, and this one could be the aggregator in the word count example. They can have different parallelisms. So one could have more parallelism than the other, depends on some restrictions or something, or maybe they can use all the system resources. But what we have in the execution level is that each consumer tasklet is actually bounded to a specific thread, which means that this consumer tasklet 2 will always guarantee to run on thread 1, so that this will not do a context switch. This is just a tasklet. It is always given to this thread, and it's always run there. But there is also other tasklets which does other things there. So they all run in a sequence. So it's like a green threading in the sense. So this is what makes it much faster. When you push it further, if there's a place to run it, it will run it. Because it's just and we assume that all these tasks are like small enough to run in a millisecond or maybe a couple of milliseconds. But of course, you are allowed to run, like we said, non-cooperative task. Maybe there are some blocking operations and etc. They need to be run on a single thread. In this case, they will have a dedicated thread, and they can do some blocking operations, like an I/O operation or something. So again, we see that we have windowing support, sliding windows, tumbling window or fixed window, or a session window, like a user session. You can say, okay, this is the start of the session, this is the end of the session. In between, everything should be considered inside the session. So do the calculation for all this, during this session, etc. We are supporting late events. So while we are, adding a timestamp, it could be a local timestamp or it could be a field inside the data. And you can also say, okay, this is my timestamp, and I want you to allow me to deliver late events, maybe like 2 seconds, 4 seconds. Of course, it will increase your latency, but at least you will receive and process those events if this is what you needed. And as I said, it is fault tolerant. It can run a very long time, and it will scale out for you. When the node just goes down, it will just be processing, start the same processing on the other nodes, and you won't lose any data. Of course, it assumes that you are not shutting down half of the cluster at the same time. And we have, as I said, exactly one, and at this one behavior. So you can actually choose what kind of processing behavior you need. Are you need speed and can lose a couple of data in case of failure, or you need to process each and every one of the data, and you can compromise the speed a little bit, because these exactly ones will be creating a snapshot for each items, so that it can be make sure that it will be it will be going and starting from the latest snapshot later on if there's a failure. So the second demo, the flight telemetry. So this one is actually a good one. I like this one very much. Let me see where I am. Perfect. So let's see what it is. So we are actually reading a data from a web stream which gives us the flight information of the planes, okay, in real time. What we are doing is actually we are filtering the, we are trying to find some, like the results based on the plane frequency and etc. So we are filtering the planes less than 3,000 feet because these are the ones that has been either landing or taking out, right? And we are calculating a linear trend based on that to understand if they are landing or if they're taking off, and then using that information to store them to different sources, like these planes are landing, or like 5 planes landed to the New York airport, and etc. And then also we have some other information on this data which allows us to calculate like air pollution and some other statistics. Let me show you that. Yes, so air pollution or noise level. And in the end, what we are doing, we are just dumping all these results to a graphite data store, and I have a Grafana already. Then we will be seeing some nice dashboard. So let's give it a couple of seconds that the job starts and read the data. And we should be seeing, okay, the data started to come out. So if I open my, let's say, I cannot see it. Let's use this one. Let me use this one again. Okay, so this is my dashboard. What I need to access is this one, flight telemetry. Here we go. So this is the dashboard. So this is the data result of the processing that is being going on in between. So it's a bit dark, so you can't see good enough, but these are the results. For example, since the last time that I've been starting the application, like a couple of seconds, 9 planes landed to New York and 4 is took off. So this is the real-time data, by the way. And there are some noise and air carbon dioxide levels based on the plane data that has been receiving on all this information. So all this is happening in the background, as we see. Again, it's just a single jet node. You can create as many as you need it if your data processing needs further processing power. So all these demos is actually available in our open source repository. So what you can just go download them and run them. This is what I did. Let me go through the all. I think we are about to finish in 2 minutes.
Different library. So you're using Java. Do you have like different client libraries?
The client libraries for the time being is only Java, but I think in the next versions it will be more than Java. So for the Hazelcast, we already support some different ones. For some testing purposes, we are also using like Python workers, something like this. So it's possible using Jython or something, some similar framework. But currently, as a recap, so the Hazelcast Jet is a high performance in-memory stream processing engine and also batch processing engine. It's a simple programming API. It's just similar to Java util streams. It's simple to deploy. It's just a 10 megabytes jar file without any external dependencies other than the connectors that you're using. It's like Hazelcast. It works in every cloud. We already have Kubernetes, Helm charts, and etc. for the Jet, so you can just easily deploy it to anywhere. And it is specifically developed for the developers, so you can get the benefit of it. So in the next version, which will be available in this month, we will have the elasticity. So when you run a job, when you have a running job, and when you add new node, it will be automatically scaled up. we'll have a rolling upgrade feature, which will be maybe you decided to upgrade the aggregation function and restart the job, so which will be inside the rolling upgrade. We will have a management center, so you can just go and see the running jobs, statistics on the running jobs, for example, how many messages that you processed in each vertex, in each steps of the data, like how many did you read from the web API, how many is filtered, how many is written to the Hazelcast, and etc., or any other data sources. So as I said, we are aiming the 0.7 in the October and the 1.0 this year. The demo is based on the 0.6.1, and this is the address that you can find all these demos. There are 8 or 9 demos. I just showed you 2 of them, but there are some other ones as well. You can just go and play with it. Any questions? No? Yeah, okay. Thank you very much.